Let's take a look at the first category, where a pipe with both ends open. The best way to sort of demonstrate that is an open cylinder. Like any type of tube with the ends open, you can even think of it like a toilet paper tube or something like that. It has both ends open, but it's a cylinder. Now, I'm generally going to draw it with a cross section like this. Now you may think, oh, that doesn't look like a tube, but this is like I'm looking at the side of a cylinder and I can see through the walls. So this is my pipe or cylinder, just looking at it from the side. This has an open end and an open end over here. Now, generally to create a sound wave in there, you'd have to move air through the pipe. So for instance, for like a flute, there's usually a hole in the top of the cylinder for you to blow into or move air across. That gets the waves moving within the pipe. So for a pipe open at both ends, for a standing wave to occur, there must be antinodes at both ends. So that means if this is the pipe, there has to be an antinode here and an antinode there. It must be antinodes at both ends. So what does this mean? I'm just going to draw a standing wave pattern. So there's a wave. Sorry, it's not the best drawn wave, but it's a wave. If you have antinodes at both ends, what this means is there are only certain standing waves that will fit and meet this criteria. So, for instance, if you take a look at my waveform here that I've drawn, I need to have antinodes are right here, nodes, etc. Take a look at this. Now, you'll notice if I need to have two antinodes, one at each end of the pipe, I can fit in this section of a standing wave. If I have an antinode at the right end of the pipe and an antinode at the left end of the pipe, and I need to fit a wave into there, looking at my waveform here, the smallest one I can fit into is given by this part right here. I'm just going to redraw this. So if I have this pipe, I'm going to cut out that section of the wave. So notice that this part that I'm circling right now corresponds to that. So I have an antinode here and an antinode here and a node in the middle. Now you may be thinking, Terry, does the sound wave actually look like that, what I've drawn in blue in the pipe? It doesn't, but it's a nice representation of it. So it's how we best represent it. Is it exactly what's going on? Does the diameter of the cylinder represent the amplitude? No, it's just a way to draw it so we see what fits in there. This is going to be our fundamental frequency, F1. That's the first note that a flute, for instance, could play. If I wanted to look at the next pattern, I still need an antinode and an antinode. So I could now fit in, I'm just going to go back up to my sound wave here. The next pattern I could fit into would be antinode to the second antinode. Now take a look at that shape. Not the perfect looking sound wave, but there we go. This would be the first overtone or the second harmonic, F2. If we wanted to look at a further pattern, I'm just going to go up to my sound wave here that I've drawn, rid of that. Here, the next pattern I could fit in is this one. So you can see I'm just increasing the amount of antinodes. So I'm basically trying to draw a nice little wave, but make sure that when I draw it within the pipe, that antinodes are at both ends. So if I draw this pattern, it's not perfect, but it looks something like that. So this is the second overtone, or the third harmonic, F3. So these are the notes something like a flute would play. Getting a standing wave in this column of air in a pipe with both ends open, you are going to get only certain frequencies to play. These frequencies are the allowed standing wave frequencies in the pipe. And these are just, once again, visual representations of that. Just before we look at the math, I'm going to give you another look at this. Okay, I'm on a website for an app here showing standing waves for sound in the columns of air. Now, what I want you to do is ignore the bottom graph, the divergence from average pressure. We don't need it for this course. What I want you to notice is in the top picture, those blue dots represent like air molecules vibrating back and forth, a longitudinal wave. And so when you excite those air molecules or get them moving, they will form standing waves. And this is an example right here of a pipe with both sides open. So like a flute. And you'll see the first graph below, there's antinodes at the end and a node right in the middle. So we're looking, there's the displacement of particles. You're basically looking at that sound wave we drew. Right now you're looking at the fundamental frequency. Let's go one higher. There's n equals 2. You can see we have antinodes at the end. Let's go higher. There's the standing wave. This is the second overtone, or the third harmonic, n equals 3. And we can keep going higher and higher. Is there a way we can determine these mathematically? So it turns out that in a pipe with both ends open, the allowed standing wave frequencies are given by NV over 2L, where N is 1, 2, 3, 4, and V is 340 meters per second, or the speed of sound in air, and L is the length of the pipe. Now you'll notice it's the same formula as a string fixed at both ends. The difference is, in a string, the speed of those waves that travel through the strings are given by the tension and the mass density of the strings, but in a pipe with both ends open, it's the speed of sound in air. In the next video, I'll tackle the case where we have a pipe or a tube with one end open and one end closed. All right, thank you for watching. Have a great day.